In previous videos, we've talked a lot about AM broadcast band radios and signals, but we haven't discussed the modulation approach itself, or modes related to it like single sideband. If you were a ham in the 1930s and 40s and operated phone, you used AM. Single sideband suppressed carrier became possible in the 1950s and quickly supplanted AM on the ham and other HF bands, while medium frequency and high frequency broadcasters continued to use amplitude modulation. In this video, we'll look at some of the math of AM in order to understand how sidebands arise. After the math, we'll illustrate the ideas with a function generator and oscilloscope in FFT mode. Let's get started. To start off with, let's consider just a simple signal. You could call it a continuous wave if you like. We'll call it a carrier in this case. And we'll call this function C of t, because it's a function of time. And the C of t is equal to a constant A sub c, which is an amplitude, times a cosine, although we could easily write a sine instead, it doesn't really matter, of 2 pi times f sub c, the frequency of this periodic function, times time. And if you plot this out as a function of, if you plot out C of t as a function of time, it traces out this familiar cosine wave. The amplitude is the distance from the maximum of the function down to the zero. And this function repeats x number of cycles per second, and that's what f sub c is. It's the number of cycles, so this would be one cycle here, here's another cycle there, and so on and so forth. So the idea behind amplitude modulation is to make the amplitude of this wave vary in time in a way that depends on the signal that you want to modulate. For example, a human voice into a microphone. And so what that means is that this amplitude here, this amplitude, is going to go up and down as a function of the frequency of the modulating signal. That's really all there is to it. But to unpack that simple idea a bit, let's do a little bit of algebra. So suppose we modify this constant amplitude A sub c to make it a function of time itself. And so we're going to keep this initial piece, this constant piece A sub c, and we're going to add on a modulation piece m of t, so that we can then rewrite the simple A sub c times cosine function as A sub c plus m of t, quantity times the cosine of 2 pi fc t. Alright, well the next step in this story is to then pick some explicit function for m of t, and without loss of generality, and we'll return to this in a bit, we're going to let m of t itself be a periodic function, characterized by an amplitude A sub m and a frequency of modulation f sub m. So we're letting this modulation be a single frequency, a monochromatic wave, if you will. And we'll see how that is not limiting in just a bit. So we substitute this m of t into the second term in the modulation, and we expand. So by expanding, we just simply multiply this cosine here times that cosine, and then times the A sub c term. When we do that, we get C of t is A sub c cosine of 2 pi fc t, plus this product term here, A sub m times a product of cosines, and the cosines are a frequency f sub m and f sub c. You say, well, that's kind of complicated, I don't know what to do with that. But in trigonometry, there's an identity, which is 2 cosine of x cosine of y, is equal to, or equivalent to, cosine of x plus y plus cosine of x minus y. And so you see that when you apply this identity to this term right here, that we will end up with cosines of the sum frequency and of the difference frequency between the carrier frequency and the modulation frequency. Okay. So if we just do that then, we get a sub c cosine of 2 pi f ct plus a sub m over 2, right? That 2 comes from that 2 right there, times the cosine of f sub c plus f sub m t, and then cosine of f sub c minus f sub m t. Well, at this point, it's usually customary to define a constant m, which we will call the modulation index, and to express that as a ratio of the amplitude of the modulating term to the amplitude of the carrier term, so that a sub m then is expressed as this constant times a sub c. And we usually take a sub m to be between 0 and 1, although it can be greater than 1. So we're left now with c of t equal to 3 pieces, a carrier piece, which is just a simple cosine and a constant amplitude, and then m a sub c over 2, using our modulation index, times the sum of a cosine of the sum of the frequencies and the difference of the frequencies. You say, well, it doesn't look a lot simpler, but in fact, it tells us a great deal about AM waves. So as I said, there's a carrier piece here which carries no information regarding the modulation. It's just, the only information per se that it carries is the frequency. But then we have these other 2 pieces, and they happen at different frequencies. They happen at f sub c plus f sub m, and we call this the upper sideband, and then f sub c minus f sub m, and we call that the lower sideband. So when m is 0, when you're not modulating, both of these terms go away because m is 0, and you're left with only a carrier wave. When m is equal to 1, you can have 100% amplitude modulation. And when m is between that, you have an intermediate percent modulation. So what does this look like in the frequency domain? Well, you could kind of guess what it looks like. You could imagine there's going to be 3 spikes. They're going to be monochromatic spikes because these are discrete frequencies, f sub c, and then a sum and a difference frequency. And in fact, that is what it looks like. If you plot out the power or the energy, similar power and energy are related to one another, as a function of frequency now, you will see a spike over here at the modulating frequency. Then you have the carrier frequency, and you have an upper sideband and a lower sideband. And this constitutes the amplitude modulated signal. And it has a bandwidth, which is given by the difference between the highest frequency and the lowest frequency in this case. So this will be 2 times the modulation frequency. And that's how wide an amplitude modulated signal is. All right, let's go back and clean up a couple dangling ends before we proceed to do a demonstration. So I said I would come back to show why simple sines and cosines are not a limiting case. And the answer to that is because any function that is bounded on a particular time interval can be expanded in what's known as the Fourier series expansion. The Fourier series is just simply representing a periodic signal in terms of a combination, a linear combination of sines and cosines, so that you can redo all the math but with sums of sines and cosines that we did above. The effect of this now is that the sidebands spread out, and they spread out depending upon how many sines and cosines you need to represent your modulating signal. So I've drawn these as kind of rectangles. This is only meant to be a cartoon, but in general, these might be smeared out in a different way. So it's of interest now to notice the width of these things, and so the bandwidth of that will be, in the case of human voice, if you're modulating with a microphone, will be proportional to the bandwidth of an audio signal. And just to get an idea of how much audio width or bandwidth typical speech contains, if you're representing the human voice in a high fidelity way, in which case it would sound like the speaker is standing next to you, then you need to capture frequencies somewhere between a few tens of hertz up to 15 or maybe even 20 kilohertz. But if you're not interested in high fidelity speech, you only need it to be intelligible, then you only need to capture somewhere between a couple hundred hertz and 3 to maybe 5 kilohertz. And in amateur radio SSB transmitters, single sideband signals are generally kept to around 3 kilohertz. But in fact, you can even chop off more bandwidth if you only look at maybe 500 hertz to maybe a couple kilohertz. You can still recognize the speech, the voice, but the fidelity is very poor, and it's hard to recognize. All right, a couple other things to note before we get on to the demonstration. Each sideband in our amplitude modulation expansion carries the same information, right? Those sidebands are symmetric on above the carrier and below the carrier, so that you only really need one of those sidebands in order to carry information. The carrier itself can be thought of as a reference for demodulating that sideband. And in particular, because it's a boring function, it's just a frequency marker, it doesn't carry any modulation information, it's very easy to regenerate in a receiver. And that's what a beat frequency oscillator is. Another thing to notice is that if the carrier is removed from the signal or suppressed, the power required to transmit that signal is no longer wasted in the transmitter. So you don't have to transmit that power. You can spend that power on the single sideband signal itself. So in terms of performance, SSB signals require much less power than a full AM signal does to carry the same amount of information. Moreover, yet another advantage of single sideband transmission is that the bandwidth is decreased without the carrier and the other symmetric sideband. So reducing the receiver bandwidth required to receive an SSB signal means that the receiver receives less noise, and so the signal becomes easier to discern out of the noise. And because of the lower bandwidth required by an SSB signal, you can fit more single sideband signals into the same amount of RF spectrum than you can AM signals. All right, let's now move on to demonstration here. And what I am going to do is show, sorry this is crooked, it has to do with the angles that I'm forced to work with here in my shop. It's a bit of a disaster with boxes and things in the middle of the floor. But what we have here is a signal that we're going to put out at 1 megahertz and 1 volt peak to peak. And first thing I'm going to do is have 100% modulation of a frequency modulator of 150 kilohertz. And I'm just doing that not to mimic an audio modulation in an actual AM transmitter, but rather to demonstrate the modulation envelope just with some waves that look nice or pleasing to the eye. Okay, so first thing I'm going to do is vary the modulation depth, or what we would call the modulation index. So let's move back over here. Okay, so there is 100% amplitude modulation, and what I'm now going to do is dial that down. So there's 90%, 80%. You see my triggering needs to be adjusted. That'll happen again here. There's 70, 50% amplitude modulation. There we go. and so on and so forth. So let me dial that back up now to 100% amplitude modulation. And what I'm going to do now is to turn on the math function. Okay, math. And I'm going to put this in FFT mode. There we go. And now I actually have to turn it on. Okay, so the first thing that we see is that because I'm not sampling a lot of data up here, I don't get very good resolution down here. But you can see a spike, and you can see that it's a bit symmetric, that there's a spike in the middle and then a couple ears on either side, or wings maybe. And so let me make the sampling better. All right. So here you can see this central feature, that's the carrier wave, and you can see the wings, the upper sideband and the lower sideband. So the bandwidth of this amplitude modulated signal is the difference between the upper and the lower sideband. If I now decrease the modulation, you can see the sidebands begin to fall away, but they don't change in terms of frequency. Okay, so that's 4% amplitude modulation there. There's 20%, and so on. Okay, and there's 100%. The next thing I want to do is show how the sidebands behave when I change the frequency of modulation. So here the frequency is 150 kilohertz. If I increase the frequency now, there's 170, 180, 190, and 200. You see how the bandwidth increases, that the wings, or the upper and lower sideband, increase in terms of separation. It's also interesting to look at how the envelope changes as well. If I decrease down, so there's 120, 100 kilohertz, you see that the sidebands get closer to the carrier, and eventually will, that's at 30 kilohertz there, and as the frequency becomes lower and lower, or approaches that of the carrier, you see that they essentially disappear. As far as the resolution of this oscilloscope in FFT mode is concerned. Okay, so let's bring this now back up a bit, and let's see, 150 kilohertz. There we go, it's what we had before. I like this demonstration. I thought it would be interesting to go through the math and show how the modulation envelope arises in the time domain by doing some fairly simple trigonometry and algebra, and show in the frequency domain how this modulation maps into sidebands. From an engineering perspective, when you design a single sideband transmitter, you usually start with an amplitude modulated signal, and then you remove the carrier in some way in one of the sidebands, whichever one that you don't want. There are different ways of doing that. There's with filters, but there are other ways of doing it too, including approaches that involve shifting the phase of the sidebands relative to one another. And there are other approaches as well. Maybe we'll talk about those in a future video. All right, I just wanted to do a quick little video on single sideband. It is conceivable that a new single sideband radio will appear in a review in the future, and it just seemed logical to talk a little bit about it before we get to that. I hope you found this useful. I want to thank my viewers for continuing to subscribe, and new subscribers as well. We've broken 1,000 subscribers to this channel. I never thought that would be possible, and look forward to producing more videos. Keep the comments coming, and as always, thanks for watching.